Hello, everyone. Um, this is section 5.1. I know this might sound a little weird. I'm going to say it's been a while since I've seen you. It's actually been a while since I've done a video. I know for you, you're getting them every day, but I took a little break. I had some done in advance, and now I'm back to section 5.1. 5.1 is the first section. Chapter 5 is the first section. After we've spent all of chapter 4 learning how to take derivatives. Now we're going to apply those derivatives. So this chapter is actually called Applications of Derivatives. So we're going to learn all the different things derivatives can do for us. We've already learned a little bit with velocity acceleration. So now we got a little bit more. So today is talking about graphs. So one of the things that a derivative can do, you may remember this from back in Algebra 2, it can help us find what are called extreme values or minimum maximum points. So these 2 points here are pretty important points. They were called turning points back in Algebra 2 honors. We didn't really focus on where they were very often because they were hard to find, but now they're very easy to find because of derivatives, right? So notice the slope of that tangent line right there is 0. So if we were to take our derivative and set it equal to 0, we could find those turning points, okay? So that's kind of the gist, the overall idea of this. So there's a couple of theorems to begin with in words that are important. The first theorem is not so important. It's just a fact that helps us learn something, because what we're going to wind up doing is what are called optimization problems, word problems, where we have to find the biggest the shape can be or the smallest the shape can be. So we're looking for minimums and maximums. So this is called the extreme value theorem. All it says is if you have a continuous function on some interval from A to B, then there's both a maximum value and a minimum value on that A to B. Nothing earth-shattering. Clearly, you could find the highest point. If I gave you a cutoff, you could find the highest point and the lowest point. We'll go back to that one. I don't know if my cutoff was, let's say, here and here. That means this would be the highest point and that would be the lowest point. Those would be extreme values. If I turn my cutoff to here, then this would be the lowest point, but then this up here would be the highest point. So the highest point could occur on an endpoint, could occur somewhere in the middle if it's turning. So that's the extreme value theorem. Nothing you really need. It's just a fact that we use. Okay, so math, this happens in math a lot where we give you these theorems that aren't so useful for us, but they're useful in the big picture to make sure everything works. The next definition is called a global extreme point. A global extreme point. Or global extrema in terms of plural. So it's either a minimum or maximum. It's just the absolute minimum value or maximum value on an interval. So I might give you an interval or a graph and say, find the global maximum point, which is the absolute highest point on the graph, or the global minimum point. The next one is called a local extreme value, minimums or maximum. So the global is the biggest or smallest on the entire interval. Local, this is kind of weird, vague definition. It's just the minimum or maximum point in a close region. And how close? Well, how close is really just these points right here, right? Any turning point would be a local extreme point. It's the highest or the lowest point in its little neighborhood. When we say neighborhood, we mean really, really close. So if it went like this, these would all be local maxes. These would all be local mins, just the highest or lowest point in the nearby. So we're going to both ask for locals as well as globals, okay? And we'll talk about how to find those in just a second. So we are going to try to find them. And I kind of mentioned it clearly that the locals are going to be found when the derivative is 0. Also where the derivative is undefined. So I'll mention that here in just a second. So the first theorem here is just if a function has a local minimum or a local maximum, or a turning point, for lack of a better term, it's going to happen when, there's a little catch here, and the derivative exists. No cusps, no vertical tangents, no corners, those sort of things. We'll deal with those also. But then the place we're going to find that local minimum or local maximum is when the derivative equals 0. All right? All of these points have a derivative equaling 0. We could deal with cusp. Clearly, a cusp is a turning point also. It's going to be a local maximum, but that's not where the derivative is equal to 0. That's where the derivative is undefined. So then we bring in this next little definition, which is called a critical point. A critical point is just a quick definition. You're going to hear this word 1,000 times in this course. It's just when the derivative is 0 or the derivative does not exist. Critical points are very important in our problems. when we have a graph, or an equation, we're going to look for a critical point, because the critical points are where the turning points are going to be, or where the local minimums and maximums are going to be. Okay, and we're going to do a couple examples here so I can walk you through. This is kind of a weird definition. It doesn't really come up very often, but I'll throw it at you. It's called a stationary point. A stationary point is a point in the interior of the domain of a function at which the derivative is zero. So stationary point is specifically when the derivative is zero, not when it's undefined. I don't ever use that term. It does pop up in the book. It'll pop up in the AP review a little bit. I've never seen it on the AP test, but just so you know, the stationary point is when the derivative is zero. So I'm going to walk through 3 examples to kind of help you see how this works and show you the algebra. You're going to do a lot of algebra in these problems. It's going to be a big, gigantic algebra test. The calculus isn't going to be that hard. It's going to be the algebra that can be a little tricky, and every problem takes on something different. So I'm just going to walk you through the process the first time. The first question says to find the absolute minimum and maximum on the interval from 2 to -3. So I'm going to rewrite down here. Give me a second to get rid of all of this. And we'll kind of rewrite the problem here, which is x to the 2/3. And the interval was 2 to -3. Whoa, 2 to -3. That's a good. How about -3 to 2? All right, so we could graph this. It'd be useful, but we're not going to graph it. I'm going to show you that we don't really need a graph. They can be helpful if you want, for sure. We're just going to go through the math. So remember, the question was absolute min and max. Absolute, which by another term is global, min and max. So the absolute minimum and maximum will occur at one of 2 places. They will occur at the critical points, or they will occur at the endpoints. So what we need to do is do the calculus that finds the critical points for us, and then do the algebra that finds the endpoints. Then we just figure out which one's the highest and which one's lowest. All right, remember I mentioned back here, if I got this little curve here, could be a global if I have an endpoint like here and here, but it could just be a local. All right, so what we do on all of these problems, we're going to take the derivative first, and then we're going to check your algebra. Okay, derivatives are going to be pretty easy. I take y prime equals 2/3 x to the -1/3. Done. I'm done with calculus. The rest is algebra. All right, so what we do now is we find the critical points, right? So the critical points are when the derivative is equal to 0 or undefined. So this thing is actually never equal to 0, but it's undefined at x equals 0. Remember, this is the same thing as this, right? So it's undefined at 0, which means there's probably a cusp there. It could be a vertical tangent. We're not going to worry too much about it. The math is going to handle it for us. So now I have a critical point. Is actually at 0, and we'll plug that 0 back in. Whoa, not to there, sorry. Back to the original function, which is 0, 0. And then we have endpoints. And the endpoints are -3. And then we're going to have we got to plug that in. So the cube root of -3 squared. So it's -3 to the 2/3. And then the other endpoint is 2, and 2 to the 2/3. Okay. So sometimes it's a little bit tricky without a calculator, knowing those actual values. If you need to use a calculator to find a value, often the numbers will come out a little bit easier. So I'm going to rewrite them. We're going to go 0, 0, and then we're going to go 3 to the 2/3 is 2.08. So -3, 2.08. And then we plug in the 2 to the 2/3 is 1.58. So it looks like this is the max global, and that's the minimum. So again, process, find the critical points, derivative equaling 0, derivative undefined. Don't forget the undefined. People forget that. And then find the endpoints, and your globals will be at one over the other. By the way, this one right here is also called a local minimum. If we were to graph this point, we got 1, 2, 3, 1, 2. We got -3, 2.08. We got 2, 1.58. And we got 0, 0. I don't know what happens in between. It doesn't really matter. So notice local global max on that one on the left. Local max here, but not global because that one's higher. And then this one, global, local min. Okay. Any global minimum maximum will also be a local minimum maximum, but not necessarily the other way around. You just got to check those points to figure that out. All right, so let's go one more here. 1 over 4 minus root x squared. So 1 over the square root. All right, notice this one doesn't give you an interval, but there is an interval because there's a domain. So one thing is I must consider the domain. It looks to me like x has to be between -2 and 2. Okay, not -2 and 2 though, because those will give us 0, and then we'll have 1 over 0. So if I were to graph this thing, it's going to have an asymptote at -2. So a little picture doesn't hurt. To see it. So I'm going to rewrite this. Actually, I know I don't let you do this on a quiz or a test to find derivatives, but this will actually help us with the algebra. So I'm going to take the derivative, which is -1/2 times 4 minus x squared to the -3/2. It's a chain rule, so times the derivative of what's inside, which is a -2x. We can simplify this, plus 2, so we end up with x times 4 minus x squared to the -3/2, or maybe we look at this as x over 4 minus x squared to the 3/2. So this is our y prime. Whoops. So y prime equals 0 when x is 0. And then it's undefined at -2 and 2 again. Those are those original endpoints from before. So they're not actually points. So notice if I take this 0 and plug it in up here, we get a point at 0. We plug in that 1 over 4, we get 1/2. So now the question is this a minimum or is it a maximum? Because I don't have any other points, right? I can come back up here to my picture. And I got this point at 0, 1/2. Okay. There's a couple ways to do this. You can think about all the other skills you've learned in all the other classes. You could also plot a couple points. You could just plug in 1 and plug in -1 maybe. By the way, it's going to be symmetrical to the x-axis, or it's the y-axis, sorry. So you could do that. You could plug in a couple points. You could also realize there's no x-intercepts in this graph. So the graph can't cross that x-axis, so it can't go down. So it's probably going to do like that. But if you're not sure, just plug in a point. You plug in 1. 1 over 4 minus, it's 1 over the square root of 3. Sorry, 1 over the square root of 3, which you can see is a bigger number because square root of 3 is less than 2. So it's a bigger number than that. So this is a local and a global minimum. Notice the graph. There is no global max because the things go up and up and up to infinity. Any graph that goes up to infinity or down to -infinity, up to infinity will not have a global max, down to negative will not have a global min. Could be locals, could be not. So that's the basic process for that. Not much else to show you there. I think that's enough. There's one more example, but if you want to look at another example, grab that book. I don't want to bore you right now. They're all kind of the same. Find the derivative, set the derivative equals 0, check the endpoints if there are endpoints. The globals will occur at the derivative equals 0, derivative undefined, or at the endpoints. So we just check those, just find all those key points. We call those key points, right? Critical points and endpoints, plug them in to figure out which is the highest, which is lowest, and go from there. So hopefully that works out for you tonight. We're on to chapter 5, applications of derivative.